Welcome to this next video in the playlist on field theory. In this video, what we're going to consider is a theorem regarding having an algebraic field extension over another field that is already an algebraic field extension of an even smaller field. And what we're going to be able to conclude is that the overall field extension from the largest field to the smallest field is also going to be an algebraic field extension. That's the main thing that we want to prove in this video. Okay, so let me now firstly state what we're trying to prove more in depth, more clearly, and then we'll go ahead and prove it. Okay, right. So what we're going to be doing then is we're going to be working with a tower of field extensions. Okay, so we're going to have just three fields initially. Okay, so we're going to have our field capital F here, we're going to have our field capital K, and we're going to have our field capital L. And they're going to be nested inside one another. So F is going to be inside K, so K is going to be a field extension of F, and K is going to be inside L, so L is going to be a field extension of K. Okay, so let me just draw a picture for this then. So we'll have L as our largest one, represented by this large box here, and let's add a bit of colour on. Okay, so we'll colour in L in green here. So L's shown there in green, and then we'll add K on. So we'll have K as a subfield of L, so now K is going to be this smaller box inside the green box here. So here's our intermediate field, K, and now let's have our smallest field, which will be inside K, so let's have this one. This is going to be F, and we'll have F coloured in orange here. Okay, right. And now the starting assumption is going to be that K is going to be an algebraic field extension over F. So this field extension here, we're going to assume that this is an algebraic field extension. And remember what that means? That means that all the elements in K, okay, the red box here, are going to be algebraic over F, which means that there will be some non-zero polynomial in the ring of polynomials over the field capital F for which that element is a root of that polynomial. Okay, so K is going to be an algebraic field extension of F, and we're also going to assume that L is an algebraic field extension of K, which again means that all elements of L are algebraic over K. So all elements of L can be written as a, well, they're the root of a non-zero polynomial in the ring of polynomials over the field capital K. What we now want to prove is, given these two facts, that K is algebraic over F and L is algebraic over K, we want to prove that L is algebraic over F, i.e. that all elements of L are the roots to some non-zero polynomial in the ring of polynomials with coefficients from the field capital F. Okay, so we want to prove that if we have an algebraic field extension over F, and then another algebraic field extension of that over K now, then the net field extension from F to L is going to be an algebraic field extension. Okay, so how are we going to prove that? That's the theorem that we are tasking ourselves with in this video. Okay, right, so how are we going to prove that? Well, what we need to do is take an arbitrary element of L and show that it's going to be algebraic over F. Okay, because after all, that's what it means for L to be algebraic over F. It means that for an arbitrary element, and we'll call this arbitrary element alpha, so for an arbitrary element alpha, which is an element of L, I need to show that that element is algebraic over F. Now, of course, going back to the base definition of algebraic, what that would entail is showing that there is some non-zero polynomial in the ring of polynomials over the field capital F which has alpha as a root. However, we know a little bit more about algebraic elements over a field. Okay, so what we're going to do is use something that we showed in the video on algebraic field extensions to help us here. Okay, we know that if alpha is algebraic over F, then it will be true that the degree of the simple field extension of F generated by alpha over F will be finite. Okay, that's a theorem that we show in the video on algebraic field extensions. We show that alpha is going to be algebraic over F if and only if the degree of the simple field extension generated by alpha over F is indeed finite. Okay? So rather than trying to show that there is some non-zero polynomial in the ring of polynomials where the coefficients are from the field capital F for which alpha is the root, instead I'm going to try and prove to you that the simple field extension of F generated by alpha has finite degree over Fi. It's a finite field extension of F. And then if I've done that for an arbitrary alpha is an element of L, then I will have proven that all elements of alpha, well, all elements of L rather, are indeed algebraic over F, and therefore I can conclude that L is algebraic over F. Okay, right, so how am I going to show you then that the degree of the simple field extension of F generated by alpha over F is finite? Well, the way that I'm going to do this, and this is not instantly apparent, okay? This is a nifty little argument, okay? It's something that isn't just instantly obvious. You would have to sit down and ponder this for a while to come up with this argument, okay? But it's not too difficult and it's quick. Okay, so the way we're going to do this is we're going to find some larger field extension of F that completely contains this field extension of F. Okay, we're going to show that that one is a finite field extension of F, and therefore this one will have to be a finite field extension of F, because of course it's a subspace when you view it as a vector space over F of that larger field extension viewed as a vector space over F. Okay, right, so how am I going to come up then with this larger field extension than the simple field extension generated by alpha over F? Okay, well, what I'm going to remember is that L is an algebraic field extension over K. Okay, so if you take an arbitrary element of L, then that's going to be algebraic over K. Okay, because of course L is algebraic over K, so the definition of that means that any element of L is algebraic over K. So that means that alpha here, my arbitrary element of L, is actually going to be the root of some polynomial in the ring of polynomials over the field capital K. And I think I'll just annotate this picture a little bit. Okay, so here is K in red here. Okay, and I'll put my alpha on here, so let's have alpha here. Of course alpha could be inside F or K, but more generally let's just have it there. Okay, it's just some arbitrary element of L. Okay, right, so alpha is going to be the root of some polynomial in the ring of polynomials with coefficients from the field K. So let's have this polynomial p of x here, and it's going to be an element of the ring of polynomials over the field capital K, and it's going to be this polynomial that is special because when we take the evaluation homomorphism at alpha and apply it to this polynomial p of x, we're going to get 0. Okay, so I'm picking my polynomial, there must exist one, and let's just arbitrarily say that it has coefficients p0 plus p1x plus all the way up to pn x to the n. And all I can say is that not all of these coefficients are 0, because this has to be some non-zero polynomial within the ring of polynomials over the field K. Okay, so not all of these are 0. It's not a 0 polynomial, it is a non-trivial polynomial. Okay, so this polynomial has the property that when we evaluate it as alpha, we get 0. So let me just write that down. So we'll get p0 plus p1 alpha plus all the way up to pn alpha to the n when we evaluate it at alpha. And note that when you apply this evaluation homomorphism, hopefully you're familiar with this now, suddenly the meaning changes. Here the additions were just symbols in between the terms. Sticking these coefficients in front of powers of x was just, you just stuck it there to create a symbol. The powers of x were just placeholders in this structure. Okay, this was just a symbol, whereas now over here, of course, this actually means something in the field capital L. All of the additions here and multiplications and raising to the power, they're all done in the field capital L. So it's changed its meaning, and now when you work this all out, you get 0. Okay, now, okay, that's lovely. We can certainly do that. That's an intuitive thing to look at because what we do know is that L is algebraic over K, and surely we do have to use that fact at some point to prove that L is algebraic over F. But how am I going to use this to generate some larger field extension of F that completely contains this field extension of F generated by alpha? Okay, well, I'm going to look at the field extension of F that is generated by alpha and then all of the coefficients from this polynomial here. Okay, remember this is just some non-zero polynomial in the ring of polynomials over the field K for which alpha was a root. Okay, it's not necessarily the minimal polynomial for alpha over k, it's just some polynomial for which alpha is a root, which we know has to exist because alpha is algebraic over k. Okay, and as I say, bear with this argument. I know it's not the instantly apparent thing to do, but it works, and it's very simple. Okay, so do bear with it. Okay, so we're going to look then at this field extension of f that contains alpha, p0, p1, all the way up to pn, so the finitely generated field extension of f that contains all of these elements, alpha, p0, p1, all the way up to pn. And by the way, note, an important point that I haven't yet pointed out is that all of these pi's, they are all elements of the field capital K, so they're all in here somewhere, P1, etc., all the way up to Pn. They're all in there, they're all elements of K, and that is important to note that they're all elements of K, because later we're going to want to know the fact that these are all algebraic over F, which comes from the fact that K is an algebraic field extension of F. Okay, right, so look at this then. Can we all agree that the field extension generated by alpha over f is going to be a subfield of this? And in fact, I might even draw a picture of this. So I'm going to not do it on this picture. I will draw a separate picture for this because alpha's in an inconvenient position to do this with. Okay, so how am I going to show this? I'll get rid of k. I won't draw k on this new picture. So we'll have L once again here, and I think I better colour code it because we're going to have a lot of different subfields in here. Okay, so here is L in green initially. Okay, and then we've got F here. Okay, so this is F, like so. So we'll have F circled in orange here. And actually I think I will put K on because we do need to have the fact that P0, P1, all the way up to Pn are in K. Okay, so I will put K back on, but I'll put my elements in more sensible positions than I did on that other picture to justify why I am drawing the same picture out again twice. So now I'm going to put alpha in this sensible position here rather than that unsensible position there. Okay, so if I now want to generate the field extension of f generated by alpha, I could imagine something like that. Okay, so this could be my field extension of f generated by alpha. And what colour should I do this in? I think I'll do it in vivid purple. Okay, so it shows up nicely. So all of that, that's the field extension of f generated by alpha. Now what we're considering is this even bigger thing, the field extension of f generated by alpha, p0, p1, all the way up to pn. Now all of those elements are elements of k, and I'm going to put them all in a nice line there. Okay, so you might now consider this even bigger thing as looking like this here, this box here. So we'll let this box be the field extension of f generated by alpha, p0, p1, all the way up to Pn here. And what colour should I colour that in? I think I'll go in yellow here, like so. Okay, right. So that's the picture for what we're doing here. We're building this even bigger field extension of f that not only is generated by alpha, but also by these coefficients p0, p1, all the way up to pn, which we got from this polynomial here. Now, more rigorously, I know the picture now shows this, but why? Give me a good explanation as to why this is contained within this. Well, remember the definition of this. This is the intersection of all subfields of L which fully contain f and contain this element alpha. This is a subfield of L that fully contains f because it's a field extension of f, and it's going to contain alpha. Okay, so this is one of the things that you're going to have to intersect in that massive great intersection to produce this thing. Okay, so this thing is certainly going to end up being fully contained within this one. Okay, so there's the more rigorous argument as to why this is truly contained within this. Now, if I could show then that the degree of this field extension of f over f, okay, whoops, a little ahead of myself, so the field extension of f generated by alpha, p0, p1, all the way up to pn, the degree of that over f, if I could show that this was finite, do we agree that I could then conclude that this, the degree of this as a field extension over f would have to be finite? Because remember what the degree of a field extension means. It means view this as a vector space over this field f. What's the dimension of that vector space? Well, this would be a subspace of this one. okay, viewed as a vector space over F. And we know that if this has finite dimension, the dimension of a subspace of a finite dimensional vector space will have to have dimension less than or equal to the dimension of the larger space. Okay, so it would have to be less than or equal to this. Okay, so I might just add that on, that this thing here, and in fact I'll just squeeze it in here, the degree of the field extension generated by alpha over F is less than or equal to this thing. Okay, that's just basic linear algebra and the understanding of field extensions in terms of vector spaces. Okay, so if I can show that this thing is finite, I can conclude that this thing is finite, and since this works for an arbitrary alpha, I can conclude that all of the alpha that are in L are algebraic over F, and therefore L is an algebraic field extension of F. Okay, so the whole problem now depends on me being able to show that this field extension of F is a finite field extension of F. And you might be saying, well, you've made this worse. That looks awfully more difficult, but it's not. Okay, what we're going to do to prove that this is finite is use the Tower law. Okay, and we're now going to find a field extension of F that's in between these two. Okay, so you might be getting totally fed up with this, the number of different field extensions of F that we're talking about, but we're now going to find one that's in between these two. Okay, so we're going to find an intermediate field extension of F that's in between F and this, and the one that I want you to look at is the field extension of F that contains P0, P1, all the way up to Pm, but not alpha this time, and I claim that that will be contained within the field extension of F that contains alpha, P0, all the way up to Pn there. Okay, and on the picture you could imagine that it's this box here, and I'll just highlight that in. Okay, so if I draw it in green as well, this thing here, so it has to contain F. It is going to be a field extension of F, but it needs to also contain those elements of K, the coefficients of the polynomial, P0, P1, all the way up to Pn. So you can imagine that it's this box here. I won't bother labelling that on, but that's what it might look like in terms of the picture. Okay, and it is indeed going to be in between these two. It's going to be a field extension of F, so that one's fine. I hope you agree with that one. It's also going to be contained in this, because remember, what's the definition of this? This is the intersection of all of the field extensions of F, the subfields of L, which completely contain F and contain all of these elements P0, P1, all the way up to Pn. This is a subfield of L that completely contains F and contains all of those elements, so it's one of the things that will be intersected together to make this. Okay, so indeed this is going to be contained within this. Okay, so that's fine. That is going to be in between the two, and now what we can do to work out the degree of this one over this one, we can apply the Tower law and say it's the degree of this one over this one times the degree of this one over this one. Okay, and we can make comments about those two degrees, which is why this suddenly all works. So now let's consider the degree of the field extension of F generated by alpha, P0, all the way up to Pn, okay, over this thing instead, so the field extension of F generated by just P0, P1, all the way up to Pn here. Okay, and then what we'll need to do is multiply this, and I hope it all fits in one line, with the degree of the field extension of F generated by P0, P1, all the way up to Pn over F. Okay, so hopefully you all agree that this thing is equal to this thing just by the Tower law, which we discussed in a previous video in this playlist on field theory. Okay, now, so if we can conclude that both of these things are finite, then we can conclude that this thing is finite, and we know that if we can conclude this thing is finite, we can conclude that this thing is finite, and if we can conclude this thing is finite, we can conclude that L is algebraic over F. Excellent. So how can we prove that these two things are finite? Well, let's start off with this one. Okay, how do you go from this field to this field? Okay, this one is a field extension of this one. It completely contains this. Okay, how do you go from this? Well, of course, all you need to do is generate the field extension of this one that contains alpha. We discussed this in a lot more detail in the video on finitely generated field extensions, that you can split a finitely generated field extension in this way into a series of simple extensions. Okay, and in this case we can write this as generate the field extension of F that contains P0, P1, all the way up to Pn, okay, and then take this field and generate the field extension of this that contains alpha. Okay, of course in that video we thought about doing this one first, then this one, all the way up to finally this one, but of course you don't have to do it that way. You can mix and match it a bit. There's no God-given law that says you have to firstly take the field extension of f that contains this one, then take the field extension of that contains this one. You can mix and match it a bit. Okay, so we can certainly do this one last if we wish. Okay, so we generate the field extension of f that contains p0 or p1 all the way up to pn, and then that's a subfield of L, and now we want to generate the field extension of that contains alpha. Okay, and that's equal to this. So now this, we can conclude that this will be a finite field extension of this if alpha is algebraic over this. Okay, because this is just a simple field extension of this. I know this thing looks horrendously complicated, but it's just a subfield. It's just this box we're imagining here. Remember, I'll just circle that even more. It's just that box. So it's just a subfield of L, and now we're just generating a field extension of it, but using a single generator. So that's a simple extension, and we know that simple extensions are going to be finite field extensions if that thing is algebraic over the field that you are you're trying to extend. Okay, so I need to now give you an argument as to why alpha is going to be algebraic over this. Well, I know that alpha satisfies a certain polynomial. Alpha satisfies this polynomial. The coefficients of this polynomial are p0, p1, all the way up to pn. Those are all elements of this field extension of f here. Okay, so basically this polynomial p of x is certainly going to be an element of the ring of polynomials over this field, which is the field extension, I've missed out p0 there, the field extension of f generated by p0, p1, all the way up to pn. So it's certainly going to be in this ring of polynomials, and therefore there is going to be a non-zero polynomial in the ring of polynomials over this field that we're trying to extend here, which has alpha as a solution. So alpha is going to be algebraic over that, which means that this simple extension here is going to be finite. So I can conclude, therefore, that this one is finite. Okay, and indeed all you'll have to do is consider taking these polynomials where the coefficients are from this field here, this field extension of f, and evaluating them at alpha. Okay, getting elements that are in the field L, collecting all of those elements together, and that will be your subfield and your field extension of this. Of course, all the elements of this will end up being in there because of the constant polynomials in here. When they're evaluated at alpha, they'll stay the same, so you will get all of the elements back. But because it's algebraic over this field extension of f here, you can conclude that, you know, when you evaluate all the polynomials in here at alpha, it won't just continue generating you brand new elements. It will loop back at some point, and therefore you will get a finite field extension. Okay, as I say, if you aren't totally comfortable with that, watch the video on finitely generated field extensions. Okay, right, now the argument comes again, so I can conclude that this is finite, this one here, this one's finite. Now let's conclude that this one is finite, and it's the same argument, just slightly more complicated. Okay, this is a finitely generated field extension of f, and I'm now trying to prove that it is finite, that it's a finite field extension of f. Now, when will the finitely generated field extension of f, a field extension generated by a finite number of generators here, when will that be finite over f? Well, we know that it will be finite over f if and only if, this is something that we prove in the finitely generated field extensions video, if and only if all of these elements, p0, p1, all the way up to pn, are algebraic over f. Okay, if these generators that you have here are all algebraic over f, then you can conclude that when you generate this finitely generated field extension of f with these generators, that it will end up having a finite degree over f. Now, why are all of these elements going to be algebraic over f? Because they're all elements of K. Okay, they're all in K, and K is algebraic over f. That's where we're finally using this bit. We use the fact that L is algebraic over K with generating this polynomial. We haven't yet used the fact that K is algebraic over f, and we must use that at some point in this argument, and here it is. Okay, it's to conclude that this is going to be a finite field extension of f. Okay, and again, the way that you'll build this thing is you'll consider all of the polynomials in n variables over f evaluated at p0, p1, or you actually need n plus 1 because you've got n plus 1 things here. You'll consider the ring of polynomials in the n plus 1 variables, x1, x2, all the way up to xn plus 1, being evaluated at p0, p1, all the way up to pn. You'll get loads of elements in the larger field capital L. You'll certainly get all of f because of the constant polynomials. Collect all of those answers together and you'll get your new field extension of f, which is this field extension of f generated by these elements. Okay, and again, because they're all algebraic over f, it won't go on forever generating new elements. It will loop back around, and therefore we can conclude that this will be finite. And again, if you're not familiar with that, and I'm sorry, it's on a bit of a slant here, I hope it hasn't been on that slant for too long. If you're not familiar with that, do watch the video on finitely generated field extensions where we go through all of this in a lot more detail. Okay, so we can conclude that this is finite and this is finite, so when we multiply them together we will get something that's finite, so this is going to be finite, so this is going to be finite, and therefore we can conclude that alpha was indeed algebraic over f. Alpha was just an arbitrary element of L, nothing special about it, so it works for all alpha as an element of L, therefore L is going to be algebraic over f. Okay, so then we have indeed proven the main theorem of this video. Okay, and of course, once you've done it just for 2 in this way, so once you've proven that, you know, if k is algebraic over f and if L is algebraic over k, that L is algebraic over f, you can do it for an arbitrary finite string of field extensions. So if you have another one, okay, what should we call it? F, K, L, should we have another one, E here? Okay, if you know that this is algebraic as well, okay, if you know that E is algebraic over L, then you can conclude that E is algebraic over F, and that's very simple to show because you can imagine, if you like, getting rid of K temporarily. Oh, well, actually, keep K for the moment. What I'm trying to say is, if we know that K is algebraic over F, and we know that L is algebraic over K, and we know that E is algebraic over L, then we can conclude that E is algebraic over F, and the reason is that you can imagine getting rid of E initially. From what we've just shown, you can conclude that L is algebraic over F, and now imagine getting rid of K, so keeping E this time, and now you know that L is algebraic over F, E is algebraic over L, and then apply the theorem again. Imagine K doesn't even exist anymore, you don't need to, it doesn't need to be there. You can now conclude that E is algebraic over F just using the exact theorem that we have used, where now L is the intermediate one, E is the biggest one, and F is the smallest one. So it generalizes, and you know, by induction this spreads on for an arbitrary finite tower of field extensions. Okay, so if all of the little field extensions are algebraic, the overall field extension is algebraic. Okay, so we'll end this video here.